Hello, my name is Clarissa Marquez, and I will be discussing over linked lists and stacks, a discussion for Lab 10. My name is Clarissa, and this is for the class Objective-Oriented Programming Lab. An overlook on linked lists and stacks. Purpose of Lab 10. Being able to discuss linked lists and stacked code. This lab focuses on understanding how the linked list and stack work behind the scene through dynamic memory and pointer manipulation. Some key structures, of course, is linked list and stacks, which we'll be going over in the PowerPoint. Focus is to understand code and memory behavior. Code structure and classes. This is a basic understanding of what you expect between linked lists and stacks. A node class stores data and also provides a pointer. With nodes, as we discussed in class, it has two parts. It stores a data and it has a pointer pointing to the next node, or null. Linked list class handles list organization. A linked list is several nodes organized with each command used in between. A stacked class builds use linked list methods. There's also related to this class is a push and a pop, which will be later discussed in this PowerPoint. Each class has a specific role, and understanding their structure helps break down how data moves throughout the program. Node class overview. A node stores one unit of data, has a pointer to the next node, and basic for linked lists. Node structure and pointer discussion. How it works. Each node structure has a pointer to the next node, becoming a pair. This is a structured data on pointers. This dynamic memory can be used both in linked lists and stacks. A node builds up on each other, which the pointer provides the user an idea where the next node is pointing to, and how in each node that follows with the pointer creates a linked list. And with linked lists, we can use stacks to build on top of the linked list, to build on top of the nodes. Example of a node code being used. As you can see on the left side, it says void insert front int value. Node dash is a node pointer. New node is an obvious new node, equal to new node value. So the new node is going to be inputting a value, so the new node pointed to the next is the head, resetting the new node as the head. Head equals new node. And right here is just in data saved in each node. Right here, creating a new node, linking the current head, updating head. Memory diagram after both inserts. Linked list at N10, linked list at N20. So the head is at the start, and then this little part is a node. It stores the data in one part, and right here is the pointer pointing to the next node. The next node is 20, and it has a null at the end indicating that either it is the end of the linked list or the node, or there is nothing stored here, so later you can add a new node. This is node 1, node 2. When insert front 10 is used, a node with data equals 20 is created, and is next pointer to set in the previous head, which has data equals to 10 to connect to the list. This is an exact illusion of how a node uses pointers to dynamically connect to the node. Linked list classes. Key responsibilities. Supports ensures insertion at the front of the list. Manages a chain of node objects. Allows list travels and prints. How it works. Using a node head pointer to keep track of the first element. Each node is linked to the next using next pointer. Dynamically grows and shrinks with new and delete. Important functions. Most importantly is to add a new node. So of course we would add insert front int value. Right here is creating a new node and providing a value to put inside it. Add a new node to the front. Print displays list from head to tail. When using this in your code, it will grab the first node and prints all its data and pointers till the end of the node or null. Clear deletes all nodes to free memory. How this is useful so it doesn't create leaks, leaks in your program, and will provide more free memory for more information stored later. Linked list destructor all calls clear. The logic for adding, removing, and managing nodes is handled by linked list class. Because it's a dynamic structure, memory is altered by as needed. So we don't need to know how big it is beforehand. Stack classes using linked lists. Core observation. For stack classes, push and pop are the main two that you should know and that we discussed in class. A push value int is adding a new node to the top. So it can be like a domino effect. You can't just take from the middle, but you can either take from the top or add from the top and keep adding from the top, or delete from the top going up to down. A pop is where you remove and delete the top node. So I was saying you could only delete from the top, not from the middle, not from the bottom. So it was a good idea to use the LIMO method, I think. And of course, display prints the current stack. So if you want to display your information, like how the stack looks, you can use this function to display. And stack cleans up memory by popping all nodes. Linked list insertion. What happens during insertion? Insertion means you're adding a new node into the linked list. It creates a new node with the value, check if the list is empty, makes a new node the head, transfers to the last node, set the last node's pointer to point to the next node. This approach lets us build on lists from the front without worrying about how long the list is. Each new node just connects directly to the old node. Linked list transversal, which can be used with printing. What is transversal? It moves through each node in the list from head to null. Allows us to access, print, or proceed each node's data. Here's an example. It's node prints and then constant node pointer to the current head, while current couts current data, current equals current next, cout null end line. Amounts. Among the most basic yet crucial operations is this one. We are unable to work with the list without transversal. It demonstrates the strength and adaptation of linked structures. Linked list deletion. What happens during deletion? It locates a node to be deleted. It updates the previous node's end pointer to skip over the deleted node. Free the memory using delete. So every time you decide to delete a node, you insert this function and it will look for the node wanting to be deleted. It will erase it and then it will free the memory, allowing more space. We are in charge of manually removing nodes in C++. While failing to do so, we can result in memory leaks, mishandling pointers, or delete the incorrect node can cause the program to crash. The stack push and pop methods. What are push and pop? Push adds an element to the top of the stack. Pop removes an element from the top of the stack. The stack follows LIFO, last in, first out behavior. So if you do think of dominoes, you start from one end and you end from the other. When you take one out from the middle, it will ruin the domino effect. So if you rather create no errors, it's best to take from the beginning and remove it. Either deleting it, which is a pop, or adding, which is a push. Since stack operates in the LIFO principle, the last item added to the list to be removed. This makes a useful structure for things to be undo operations, functions, calls, and evolution expressions. Here's an example of a push operation and a pop operation. Here, as you can see with the nodes on the side, it's creating a new node, linking to the top, and updating the top to the new node, which becomes like the head. For the bottom, it saves current top, updates top to the next node, and frees memory. Stack empty and LIFO behavior. What is LIFO behavior? Last in, first out. Last in, first out means the last element added to the stack is the first one to be removed. The stack operation operates on this principle. Think of a stack of plates. You add a plate from the top and you remove a plate from the top. How to check if the stack is empty? The stack is constantly empty when the top pointer is null. The empty function can be used to check if the stack has any elements. Here's an example of the stack empty function. Here is the LMO behavior, LIFO behavior in action. Right here you can see just a little example. It's just an example, not really a code or anything, but they are adding to the top, which is 10, and then on the next line they're adding to the top 20, and then on the next line they're adding to the top 30. And notice how it's going on top and pushing to the side. Just imagine it to be straight. So this would be on the bottom, and then 20 in the middle, and 30 on the top. And if they wanted to add a new one, it would be 40, 30, 20, 10. And for the pop, it's the same thing, 10, 20, 30, 40, but instead we're removing. So then we're removing the 30, so now it's only 20 and 10, and then we're removing the 20, which is leaves the 10 on its own. And then you could remove the 10, which leaves the stack at null. The stack is empty. The big three. There's a goal. Knowing what copy constructors, assignment, operator, and destructors do. Whenever you decide to use this, which you should, just to check on your code, you should always decide to use all three at once. For the first one, a copy constructor is a deep copy of the list. Between its other competitor, it creates a copy which can be edited, but with its competitor, it doesn't allow changes because if you do decide to change, it affects both copies. As for this case, one stays how it was from the start, how you copied it, and a second one, if you decide to change anything, stays with its edit. Assignment operator handles cleanups plus copy to prevent memory leaks within the deep copy. A destructor frees all memory to avoid leaks to prevent memory leaks. These three functions are essential when your class involves dynamic memory, preventing shallow copies and memory leaks. Empathizes that without these, deep copies wouldn't work correctly and make current crashes or leaks. Memory and pointer management. What is dynamic memory management? Dynamic memory is alternated during runtime using a new and delete. Memory is allocated for each node in the linked list or stack, meaning we can grow or shrink structures as needed. It is crucial to free memory properly to avoid memory leaks. A pointer management. Pointers are used in linked nodes together, which is node little dash next. We currently maintain these pointers to ensure nodes are connected. The memory is freed when nodes are removed. Null safety allows set pointers to null when necessary. When deleting with pointers, always make sure to manage your memory carefully. Failing to delete nodes properly can lead to memory leaks, which slow down or crash your program. Always ensure that after using a pointer, it is either properly deleted or set to null. Reflection. What I thought was most interesting was using linked lists to impact stacks. I thought it was cool how each node helps form a linked list, and linked lists helped impact stacks. Comprehending memory, delocating, and destructing logic is the most difficult. Trying to understand how memory works within the program when deleting nodes or adding nodes, it was a little difficult to just get the idea in my head, but after discussing it and learning a little bit more, I understood it a little better. Final thoughts. Linked lists and stacks form the foundation of most data structures. Understanding memory behavior is crucial in C++. Thank you so much. You have a great day.